Hello, everyone. This is lecture 14 of PTRE 475-575, well completions and advanced stimulation techniques. We had the exam 2 days ago. I think all of you took it by now. And I did give a look at the exam. There were some surprising aspects. Yeah, 8 out of 8 submitted. So thank you for all of you for taking the exam. I did skim through them, but not in great detail. There were some surprises. Like there were some questions that I expected at least somebody from the class to get it. There was at least 3 questions where almost, if not all, got it wrong, which is surprising. But some others are more okay. We'll see where the grade stands once it's been graded. Probably this spring break. Homework 2, of course, was graded, and you should have a grade for homework 2. Homework 2 grades were excellent. Homework 2 grades were excellent, so it cancels out some of the bad grades from homework 1. But I think from my first impression is that the average grade for the exam 1 will be quite low. So we'll try to make it up in the second exam. And this is why I have the class with 2 midterms and not 1. I was debating it this time because it's a 75 minutes lecture and I have to give a 75 minutes exam. I thought about doing just 1 midterm this year. But yeah, I mean, it's better if that's why I'm doing 2. So you guys have the option to recover if things didn't go well. So, common mistake was question number 6, where I was asking basically a situation where the League of Tests won't give an approximation for SH mean, or it won't be good for that. League of Testing would be a bad idea. And I did mention in class at least twice that with some variation in the context, I'm pretty sure that League of Testing is not specifically measuring SH mean, it's measuring S3, the least compressive in situ stress. SH mean is the least compressive in situ principal stress in strike slip and normal faulting. In reverse faulting, SV is the least compressive stress or the overburden. So if you do League of Testing in a reverse faulting stress environment, you're really measuring overburden, an approximation for overburden. So that was, I think, botched by everyone, which don't worry about the numbers. Just make sure that the number that you're going to get, the score, is the highest that you can get. And the other thing I will worry about myself. So if the grade looks bad, if it's bad for everyone, don't worry. It means that there would be some sorting out done at the end of the semester. So don't panic after you see your grades for the first exam. Okay, that question I think nobody got right. Another question that was common error, I think, I'm not sure if everyone didn't get it right, is that if I do this, okay, I have a pipe. I can't even draw it with the shapes. Tubular, okay, and my outline, look at that, okay? I'm giving you, let me make it empty inside or All right, no, empty. Let's make it off-white so that we can take. And I told you, I'm giving you the outer diameter. Okay, good enough. I'm giving you the outer diameter. Okay. Outer diameter. And then I'm also giving you the wall thickness, T equals, and I gave you the wall diameter. Actually, not question mark, because I gave you the values. Like, for instance, let's just put numbers on it. Outer diameter 4.5, thickness 0.25. Okay, what is the inner diameter? The inner diameter, I mean, it's common sense that the inner diameter is going to be outer diameter minus 2 times the thickness. I have a thickness here to worry about too. Many of you, if not all, did OD minus T. So it should be like 4.5 minus 0.5, so 4. Not many people forgot the 2. That's a common mistake. And another common mistake was that several of you got a question, a small question at the beginning wrong. Is that I don't, and that I'm kind of inclined to blame myself. I did mention it implicitly in class, but last year I made it more clear than the year before. But when we do decisions, technically related decisions, these are not done by vote. It's the expert making the decisions. And you're trying to help the expert or designate who the expert is. It's not like a democratic system and we all take a vote for what kind of casing we are going to run into our web. The decision is delegated to the right people to make that decision based on the available information, the best decision based on the information available. We don't go around the room, say our opinion, and vote for what kind of tubular we're going to run into the web. Anyway, so those were the most common mistakes that I saw skimming through the exam, but don't worry about them. Just try to focus and do better on the second one. Don't worry if it's not a very good grade on the first one. Obviously, some people need to be following what's going on in the class a little bit more closely. There are details that are important that can be missed. Especially, I mean, I don't really know how everybody's watching the lecture. Are they watching the video? Are they playing the video in the background and not paying attention? Are they playing in double speed? I don't really know. Everybody has their own system, but you need to get to the point where the system works. I mean, right now we don't have anybody online, which is interesting. But yeah, I mean, I need to understand that you need to understand what we say in class. Anyway, but don't worry. We'll see when the time comes, when the results come, what we are gonna do. But try to do better on the second exam. Let's try to do better on the second exam. And by then, I think you guys are gonna be more adept at with how the class is going. Anyway, so before we did a review for the exam, we stopped at 36 slide, slide 36. Perforating operations, which is an important part of well completions, actually. We need that for fracturing, especially multi-stage treatments, and so on. Also, we want to reduce the sanding potential through perforations being smaller than the wellbore, so it's harder for the sand to get into the wellbore. And also, there are some techniques we can use that involve oriented perforating, orient perforations intentionally at certain direction in order to achieve something favorable during the hydraulic fracture treatment. These techniques are called oriented perforating, aligning intentionally the perforations in one direction. Ease of application of chemical treatments, especially those treatments requiring diversion, such as scale squeezes, acidization, and other chemical dissolvers. Those are going to go through the perforation, so they always help. Bullet perforating is an old style of perforating. It's a real gun, basically, or a perforating gun that you basically shoot bullets into the surrounding rock formation. The problem with that, the main problem with that is the bullet itself. It's a solid piece of equipment that cannot evaporate or cannot, it would be there, basically blocking fluid flow into the perforation tunnel. And the tip of the perforation tunnel has been argued to be quite important. Some people believe that the base of the perforation tunnel is the most important, and some others believe that the tip of the perforation tunnel is very important. The truth is that both of them are important for different reasons at different situations. An early perforating method that used hardened steel bullet or projectile propelled by an explosive charge to create a perforation tunnel. Yeah, not easy to dissolve or get away with, remove from there. This method creates a low permeability crushed zone and leaves the bullet and associated debris jammed at the end of the tunnel, which basically makes the end of the tunnel ultimately useless. This is how a steel casing tube looks like after being hit with a perforation. By the way, when a perforating gun arrives on site, everybody turns off their phones because they can accidentally activate it. If they activate it near a real person, on the surface near a person, a standing person, etc., it might create quite a bit of damage. And by damage, I mean death, if not worse. This is how it looks like. As you see, the bullet is pretty sizable. And it's going to take a big portion of the tunnel. You have to perforate, shoot through the casing, the cement shed, and then as far as you can into the rock surrounding adjacent rock formation. It's fairly easy to understand how it works. It's also the way the bullet moves and pushes the rock, crashes it, pushes the rock into the rock. It's causing the permeability to decrease in that area. And that is some sort of what we call formation damage, okay? Which is, we're gonna learn in module 4, formation damage in more detail. It's basically altering the permeability of the formation unfavorably. The opposite of formation damage is stimulation. When I'm hydraulically fracturing a well, I try to improve the permeability in that near wellbore region. Formation damage is the opposite. Another kind, a more modern kind of perforation is jet perforating. This is basically, you have a high order explosive, which will basically release a lot of energy into the rock or casing, cement shed, and rock, and break them. Or like create a perforation tunnel through them with a shaped explosive charge. It's a high pressure jet that penetrates the casing or liner to shoot into the reservoir formation through the cement shed. The shaped charges are contained in a perforating gun assembly that can be conveyed on wireline tubing or coil tubing, depending on the application and the wellbore conditions. Now, all the stuff that we talked about earlier, like parachutes, tractors, etc., they are very well used for transporting perforating guns down long laterals when the gravity cannot be of help. The process is pretty simple. I mean, you just detonate the shaped charge, and then it basically explodes into the what is adjacent, solid layers adjacent to it. This is how it looks like. You have a detonating cord inside the gun. You have the case, conical liner, primer, which is what's gonna detonate, and then the explosive part. The explosive energy of the detonation is focused on one direction by a conical case, reflecting a lot of energy back to into a narrow pulse. A lot of research and development is done on these items, and it's done on this equipment, and they are constantly evolving and becoming better and better and better. That's how we end up from bullet perforating with bad debris that we had to deal with to these modern day jet perforating techniques. The relatively thin charge liner also plays a critical role by systematically collapsing and emerging as a high velocity jet of fluidized metal particles. Yeah, I mean, self-explanatory. High velocity jet is basically what you are trying to create. The pulse moves out at around 30,000 feet per second, which is about 20 miles per hour, and generates pressures between 5 and 15 million psi. Just as a rule of, for comparison, is let me tell you that rockets to escape the Earth's atmosphere, they have to be traveling at about 18,000 miles per hour, which is about the jet perforating, the high energy jet moves even faster at 20,000 miles an hour. So it's very, very like a rocket. Oh, the rocket moves like a bullet, I guess, or a jet, perforating jet. But yeah, it's the pressures generated are huge because there is pressures generated over a very narrow region or cross-sectional area, very narrow, and over very short time period. So the energy release is huge. The pressure applied is also huge. Tremendous. Millions of psi. This is a step-by-step process. And fired shaped charge before it's activated. The charge detonates, liner begins to collapse, high pressure jet forms, pressure wave travels at 8,000 feet per second and 7 million psi. jet becomes more developed, pressure causes jet velocity to increase to 23,000 feet per second. Jet elongates since the back of the jet travels at a slower velocity, so the jet becomes longer. That's how it's designed to work. Jet is finally fully formed. Tip of jet pierces and compacts the casing, cement, and formation with 5 million psi of pressure, which is this is from the petroleum engineering handbook, I believe, this figure. Yeah, that's how it goes. A lot of technology involved in perforating, which is, I would say, an operations-oriented topic. Um, This is another schematic that is very helpful, but bear in mind that this schematic is like perforating the top of a horizontal lateral. So the perforation here is really going up. I couldn't flip it because of the labels. I didn't make this. I did not make this figure, of course. But anyway, you have the wellbore fluid is basically brown, and you have it. This one is the wellbore fluid. What else? We have the gun. You have the liner. Here, you have the explosive is the gray. The booster is basically the primer. Detonating cord, the housing, steel, mostly steel or a certain alloy housing. And basically, the jet created, as you see, is penetrating the steel casing, the cement, and the rock formation as much as we can. Now, yeah, imagine the well is like this, and then you are perforating up. This is how this schematic is. Yeah, I couldn't flip it because of the labels. Shape charge selection, again, this is not going to be done by vote. This is going to be done by the people who can make these kind of decisions, who have the knowledge on this particular topic. There is nobody on the rig that can do all the decisions. Nobody, not even in the office. Okay? But as long as the decisions are delegated to the right people or to the right person or group of persons, I guess, group of people, it's okay. What you cannot do is hear everyone's opinion and take a vote. It's not a democracy. There are different types of explosives varying in explosive power and temperature stability, obviously. Perforation considerations, including perforation diameter, length, phasing, and shot density. These are all things that you can play with to make them more, to either mitigate a certain outcome that you don't like, or it does trigger something that you would like to see, etc., etc. Cost and availability may also be a consideration. Cost and availability It always plays a role, especially if you are a small operator. I used to work in West Texas for small operators. Like they would go cheap. They would go cheap as much as they could. And I understand it. I mean, small company from Dallas, like 10 people company or 4 people company. I mean, you don't expect them to be spending the same amount of, to have the same equipment as ExxonMobil, for instance, in a well, even if they are drilling next to ExxonMobil. So as a result of that, they are not going to have the same issues as they are drilling at ExxonMobil. It doesn't mean that ExxonMobil will won't have any issues, but it might be of different nature. And of course, I'm just using names for the sake of examples. Given that the explosive power generally detonates with the more high temperature stable explosives, a balance is required for the selection of the appropriate explosive. Perforation guns. A device used to perforate oil and gas wells in preparation for production, containing several shaped explosive charges. Perforating guns are available in a range of sizes and configurations. The diameter of the gun used is typically determined by the presence of wellbore restrictions or limitations imposed by surface equipment. Again, whoever is going to make the decision needs to consider everything that is relevant into his decision-making process. You cannot bring a perforating gun to a well without being able that the conditions are not satisfied such that the gun can be used. Then you are going to bring something that is effectively useless on location. You have to bring it back and bring the right one, which means somebody's going to lose his job, his or her job. This is how a perforating gun look like. Look at the charges. They are all facing in different direction. They are basically at an angle to each other. Here we have shaped charges detonating cord, which is what activates them or triggers them. Each charge points in a different direction from its neighbors, and generally 1, 2, 3, 4, 5, almost 6, 7. You want to see maybe these and these are the same. So 1, 2, 3, 4. Maybe every 4 or every 6, it goes like around. If it's every 4, it means 360 divided by 4, 90. If it's 6, 360 divided by 6 is 6. Every 60 degrees or every 90 degrees, you're changing basically. Every shape charge is at 90 degrees from the above one and the one below, or 60 degrees, depending on the shot density that we want. Well, not the shot density, the phasing that we want. Now, shot density is how close they are. Like shots, perforations per feet. That's the shot density. If this is basically 10 feet and we have 1, 2, 3, 4, 5, 6, 7. 7 divided by 10 is the shot density is 0.7 feet per feet, shots per feet. Many times, the perforating gun is built on location. This may create logistical issues if changing the design on the fly. You need to have enough to build the design that you like. Otherwise, again, you have to get the expert, go back to the company's headquarters and bring more stuff. You don't want that. Also creates a shift of responsibility from field to shop if they are not built on location. Okay. Now, this is how a typical perforation tunnel look like, or a properly done, as expected, perforation tunnel. You are damaging the casing. You are basically making the steel provide these little, it moves out of the way for the perforation tunnel to be created. It creates this little lip of the perforation of the casing around the hole. It's called burr, small burr. It's basically the lip that is created. Generally, if you go as you go from casing steel to cement, the perforation diameter will increase. Why? Because the cement is weaker than steel. And then you can make the argument that the cement is the same as rock, or more or less the same, or if not the same, very similar. So the change would be smaller afterwards. Going into the formation, many times perforations are designed for maximum penetration at the expense of perforation diameter. Then you care more about diameter than length. Sorry, length than diameter. But it can be the vice versa. In fact, I care more about what happens at the perforation base more than what goes on at the tip. As a mostly hydraulic fracture guy, that's what I care about, because the fractures won't start at the tip. They will start at or very close to the base. Perforation length dependent on charge weight, type, wrong strength, gun clearance, and fluid. Obviously, the bore is outside of the casing, okay? And it will be like that. You expect it to be like that because the blast of the gun is coming inside. What are the objectives of a perforation? What do we try to achieve with perforation? The aim in most cases and perforated completions is to generate the maximum perforation length, deep penetrating charges. I don't necessarily agree with that. There are people who care about the diameter or the base of the perforation more than the length of the perforation. This is achieved by a relatively tight conical geometry of the shaped charge. For some cases, such as limited entry stimulation, we're going to talk about that. Even with deep penetrating charges, the entrance hole diameter becomes critical. Okay, limited entry. What is the limited entry? So this is a collection of techniques considered. The idea started in 1969 with an article in the Journal of Petroleum Technology. Very nice article by somebody called Lagron and Rasmussen, 1969. The idea is that as I'm making, it was for vertical wells back then, but the idea is that if this is my well bore, and then this is my formation, and this is is another formation and another. This is my well bore. And there is perforations on each side, like here. The idea is that there might be a preference for the fluid that is following the path of least resistance. The fluid may want to go to on one zone, say the orange zone, than the blue zone, or the blue zone instead of the orange zone. Limited entry techniques, not necessarily for stimulation, but they will try to even the distribution out. Okay, now for stimulation, limited entry design nowadays is so that fluid, no fracture perforation cluster is left without fluid. You don't want to have a situation where all the fluid goes to the same perforations and generates one gigantic fracture that keeps growing and growing and growing. Whereas if you had a limited entry technique in place and properly working, it will even the distribution of fluid throughout those perforations. Over-perforation may obliterate the casing, cement bond, and create a microannulus. If you shoot the casing too much, it will destabilize it. Mechanically speaking, in particular, but also chemically speaking. I mean, the more you shoot it, the easier it is to come loose. So I'll be very careful. Sometimes you don't even need to do perforation. You use a slotted liner. So when you run casing, the casing already has holes in it. But it's not always the best option. In other consolidated formations, the perforations are normally limited between 180 to 120 degrees of the well to avoid sloughing of formation from the high side of the hole during production. So yeah, I was gonna say 180 is basically every 3 perforations, you are back to 180, 240, 360. And then common practice to choose is a 60-degree angle facing, that's the most popular, to minimize tortuosity and prefer initiation direction. Now, 60-degree is like every 6, you are back to where you start. Facing at every 6, every shaped charge is facing the same way as the 6 before, after it, and the 6 before. Perforation debris is very, very important. Regardless of what technique you are using, you have to deal with it. So you need to either dissolve it or remove it mechanically in a way, or you don't want it to block your perforation tunnels. Now, the perforation tunnels are narrow. They can be blocked very, very, very easily. So I'll be very careful. Very, very careful. Pieces of charge cases, loading tubes, and alignment equipment are generated by firing gun that can be debris. They may or may not be left inside the well, can plug the perforation, tunnels, and then you need a job called acid wash to clean them up before starting the fracture treatment, which is a very common situation. in the US. By the way, all those are good topics for you guys to choose a topic, a theme. All those are good themes to find a topic to write your term paper on, right? It's just you need to find a topic within a certain theme and then narrow down to the hypothesis and say how you are going to test to have the hypothesis approved or disproved. And if it keeps getting disproved, as F. Bailey said, it tests a new one, until you get one that starts working. It becomes a theory. And once it starts working all the time, it becomes a principle. Now, this is how we spot acid to clean up the perforation tunnels. And many times you have a bad situation and you are relying on a good acid job, acid wash, to clean them up so that you can do good, like a hydraulic fracture treatment from there. Oftentimes, acid is run before a stage, a frac stage, I would say, to help clean up perforations and remove skin from cement. Nothing new. Normally, acid is run before the actual frac operations. We call that acid pre-flush. It's not exactly the same as acid wash, but it has similar objectives. It's becoming common practice to spot acid during a wireline operation as well, during a wireline run, which eliminates the entire wellbore of fluid, an entire wellbore of fluid volume. This process is made possible by the invention of hydrochloric replacement acid, HCR. HCR prevents corrosion of wireline equipment, so the equipment and acid can be in the wellbore at the same time. It's how do you say, not anorganic, it's an inorganic mixture. Hydrochloric replacement acid is like people came up with this anthropogenically invented mixture that basically can work like a hydrochloric acid, but has some advantages, tries to eliminate some of the disadvantages, etc., etc. One of you guys may work on this kind of stuff after you guys graduate, and it wouldn't be a bad job actually. This process allows for decreased pumping rates using the frac spread, which decreases cost, reduces a wellbore volume of fluid. If you are using fresh water, this can lead to substantial cost savings. You will have to make a few wireline runs and record the volumes before you begin, just like in the homework. These will be pumped down volumes and will not be equal to the flush volume. The pump down volume will depend on how fast wireline is running whole, drag on tool string, bypass around a tool string, etc., etc. After a few runs, you should be able to establish an initial pump down volume and hopefully a trend in the pump down volumes. So we'll see. We'll see how those work. It's a little bit more complicated than what you have for the homework, because there is fluid that is used to fill up surface equipment. We call that slippage on the surface, like the volume that is needed to fill up surface equipment. So it needs to be subtracted to see when you try to estimate how far down the well this special treatment has made it. This is important because you need to know at what volume to pump the acid from the surface. For example, if it takes 700 barrels to pump the tool string at the plug setting depth, and the pipe volume is 500, you will displace the previous zone before getting the tool string to the bottom. Volume concentrations during acid spotting. The spot acid to spot acid at any desired point in the wellbore, just like you did in the homework, this equation must be true. Volume of pre-flush should be volume of pump down plus safety factor volume plus volume of flush. Where, V pre is the acid volume pump before the pump down. VPD is the pump down volume. VSF is the desired safety factor volume. And V flush is the wellbore flush volume to cement setting depth. All volumes must be in consistent units like barrels, BBL, abbreviated by BBL. Volume concentrations during acid spotting. Let's do a little bit of sign convention. You have fluids going in the well, downhole, and fluids coming out. You need to take both into account. The sign convention is such that negative indicates fluid volume to be pumped, including acid, before starting pump down, and positive indicates fluid volume to be pumped, excluding acid, after starting the pump down. This procedure requires performing at least one pump down in advance. This can establish how much fluid it takes to pump before the wireline tool string reaches the desired depth. So you want to pump down volume to see how far you can go, basically. The difference in volume between the previous and current pump down is assumed to be negligible. The surface line volume is also assumed to be negligible. The previous pump down volume for an acid spotting job is 400 barrels with the flush volume plug setting depth at 300 barrels. Calculate V pre for a 50 barrel safety factor. Remember the equation that we use? Do we know PD? 400. Do we know VSF? 50. Do you know V flash? 300. So 300 plus 400 minus 50. So 650. Oh, sorry, what am I saying? This is negative. Minus 400 plus 50 plus minus 300, so 150. I'm sorry. This means that 150 barrels of fluid needs to be displaced during the pump down before pumping acid. Hence, if acid is clearing the well ahead at 150 barrels on the flow meter after starting to pump down the wireline tool string, we can expect to pump approximately 250 barrels VPD minus the pre-flush before shutting the pumps down. This puts the acid 50 barrels short of the V flush. Yeah, because 50 and then 250. Once the operations are lined out, VPD tends to decrease by a few barrels per stage, right? If VPD, from example problem number 4, was 300 barrel and V flash was 400 barrel with the same 50 barrel safety factor, what would V pre be? And remember, we said V pre is pump down volume, so 300 plus safety 50 minus 400. So 350 minus 400, I think is minus 50. This means that 50 barrels of acid are necessary before starting to pump down the wireline tool string. So procedurally, pumping 50 barrels, including acid, then a 300 barrel pump down will leave the acid 50 barrels short of the volume to the plug setting depth. Any questions on perforating? Sorry, spotting acid. One common mistake is that people think, and now you know about casing and tubes and packers, most of the time spotting acid is not done through tubing, it's done through casing. Now we're going to enter another, the second to last subtopic of this module, and that is sand control, cased hole section. We learned that there is numerous ways you can keep sand out of your well, using a gravel pack as a filter, using other equipment as well, etc., etc. Let's discuss it here. Numerous tools to control, i.e. suppress, minimize the production of sand, which is harmful to equipment, both on the surface and downhole. Liners, slotted or pre-drilled, and we're going to see pictures of those, are one of the most common ways to prevent sand from entering the wellbore and downhole pumps. We call that fines migration. It can be terrible for your equipment on the surface, as well as downhole. It is not easy to get them. Although these are effective, they can cause problems as they may become clogged themselves and need remedial work. Like this is one example. The liner is prepared with multiple small slots, then set across the production zone to provide wellbore stability and an intervention conduit. So this is basically these holes are longitudinal to the axis going through the well. We call it Z, it's vertical. But there might be other cases where you will find that these kind of fractures of liners are better. The slotted liner is machined with multiple longitudinal slots. Several ways you can skin the cut and make the liner to work the way that you like it to work. Pre-drilled liners, you see a picture here, how it looks on the inside as well. The liner or screen mechanically hold back the movement of the formation sand. There are many variants of open hole sand control. The three most popular choices being standalone screens, open hole gravel packs, expandable screens. Here is an example. With A, we have a wire-wrapped screen, I wish there was one with slots to be transferred than vertical. A here is a wire wrapped screen, B is gravel pack screen, C is premium screens. D and E, and expandable screen F. And unexpandable screen F. Ten more slides for this module. Wire wrap screen. Use a spiral welded corrosion resistant wire wrapped around and drill base pipe to provide consistent small helical gap. The jacket is fitted over the perforated base pipe and welded to the pipe at each end to provide structural support for high mechanical loads. So you have the jacket as a shield. There is bigger holes behind the jacket, but the jacket acts like a shield, stopping fines from migrating into the web. These screens provide more open flow area than slotted liners, increasing flow and productivity. Here's how it looks like. RIP is the name of the solid that keeps the shield, the jacket, I guess, and the perforation inside safe. RIP wire, screen wrap wire. Perforated base pipe, inner screen, support rib, gravel pack, outer screen, inner screen, etc., etc. Best base pipe, which is normal casing with holes in it. Inner drainage layer, sun control layer, premium series weave pattern, 2 layers, so 2 shields. Outer drainage layer is always coarser than the inside one. Other types of screens that we could consider: premium screens use a woven metal cloth like the one that you wash the kitchenware at home, I hope, wrapped around the base pipe. Is like a woven metal. It's like you surround it for its own protection. Expandable screens are run to depth before being mechanically swaged to a larger diameter. Ideally, expandable screens will be swaged until they come in contact with the wellbore wall. Pre-packed screen is built with an inner screen, a layer of unconsolidated gravel placed around it, and an outer screen or shroud. Okay, so that about the screens. And I know I'm going fast, but there is no audience. Trust me, questions. But yeah. Now, if there is no questions, we are gonna move to, that will actually be the second to last topic of this module. I think it's this one, then another one, and then it's that. 3 common multi-stage stimulation techniques. This is a very important slide because I give you 3 videos. One for plug and perf completions, one for ball activated completions, and another one for coil tubing activated completions. And they are made by somebody called Aaron Barton, I believe, from Mississippi State University, who was extremely smart and very good at making animations with PowerPoint. And he gave us lecture, I think, a guest lecture when I was at Louisiana State University. But his explanations are very good and very easy for non-practitioners to understand. So let's see the first video, the easiest type of completion.
No.
If you cannot hear the video, I provided the link and you can hear it at home. It's just I don't know. I can hear it, but I don't know the people online if they can hear it or not. A very, very smart guy, Aaron Barton. And very, very simple and basic technique for the plug and perf. Basically, you isolate a stage, you pump the fractures, you move on, you make other perforations in another stage, and then you stimulate that stage, etc., etc. You start from the toe and you work your way towards the heel of the lateral. Remember when I told you the toe of the lateral is this part that we see here. If you see my mouse, that's the toe. And the heel is down to the left at the beginning. So you go from the toe all the way to the heel, and so on. The second method, is ball activated completions, which take a little bit longer. It's a little bit more difficult to understand, but it's still possible, of course. So very nice video again. And yeah, I think it's time. We'll carry on after spring break on St. Patrick's Day, I think the 17th of March. So use the spring break wisely to get some work done on your term paper. There is no homework due, outstanding homework due. We are going to be grading your exams, and I will see you when I come back. And we are available by email, me and the TA. And with that, thank you very much. Have a good rest of your day. Have a nice weekend. Have a nice spring break.